Hi everyone, and welcome back to the Towards Data Science podcast, and today we're talking about an algorithm called data2vec. And if that name sounds familiar, it's probably because it made quite a splash in social media and even traditional media when it came out about 2 months ago. It's an important entry in what's now a growing list of strategies that are focused on creating individual machine learning architectures that can handle many different types of input data, like text, image, and speech. Now, most self-supervised learning techniques involve getting a model to take some input data, say an image or a piece of text, blacking out different components of those inputs and predicting what is in the blacked out components. And that works well in many contexts, but it also means training models to perform tasks that are very different depending on the input data type. Filling in blacked out pixels is quite different from filling in blanks in a sentence, for example. So what if there was a way to come up with one task that we could use to train machine learning models on any kind of data? That's where data2vec comes in, and joining me today is Alexei Baevski, a researcher at Meta AI and one of the co-creators of data2vec. Now, Alexei actually has a long history in machine learning. In addition to data2vec, he has been involved in quite a bit of pioneering work on text and speech models, including wave2vec, which was Facebook's widely publicized unsupervised speech model. Now, Alexei joined me to talk about how data2vec works, what's next for that research direction, as well as the future of multimodal learning on this episode of the Towards Data Science podcast. I've been looking forward to talking to you ever since the data2vec paper came out and was announced to much fanfare. Obviously, it's a very, very important piece of work and very, I think it offers us a very good lens into the present and future of machine learning and machine learning techniques and training protocols. So we will be diving into all that, of course, but I do want to start by understanding what brought you to this space. I mean, this world of multimodal learning, this world of transformers and scaled models, all this stuff, like what drew your interest to AI and then specifically to scaling and training protocols?
Yeah, so I mean, I've been interested in programming ever since I was a kid. I think I started when I was like 11 or something like this. And when you program, you always write very specific instructions for the computer to follow. And I've always been interested in trying to automate away as much of this as possible. And I look at AI as a way of designing programs that are generic so that they can work on a variety of different data without you having to specifically code in specific edge cases. So, I mean, my background, I don't have a PhD in AI or anything like this. My background is computer science degree from University of Toronto. And after that, I spent a bunch of time working as a software engineer for different startups, financial companies, and so on. But throughout this whole time, I've been very interested in AI, and I had a bunch of homegrown kind of self-driven projects to explore the space, but nothing that I could really apply commercially or anything like this. Once I joined Facebook, which was over 5 years ago, one of my motivations of joining Facebook was that it's one of the leaders in developing new AI algorithms. Mm-hmm. So once I joined Facebook, I spent some time working on production teams, improving spell corrections, query suggestions, and things like this. That allowed me to see what industrial scale AI looks like. And after that, I moved to FAIR, which is now Meta AI Research, I suppose, where I wanted to work on developing brand new algorithms and trying to improve state of the art of existing techniques. And when I joined, there was in FAIR is quite unique in the sense that you have a lot of freedom to choose which area you work on. So the way I looked at it is I wanted to work on something that creates the most impact. So if I improve some particular algorithm, that it improves, not just for one specific use case, but across a wide different sets of use cases. And this is how I got into self-supervised learning. We started with text-based learning. So we had this model called the BiTransformer that was developed around the same time as BERT. Before BERT came out, it was somewhat similar. Actually, a lot of Facebook internal things used it for improving results for some time before they all switched over to BERT. After that, we moved into speech. It seemed like a related field, but also more interesting because you have continuous inputs, while at the same time, the content is very similar to what text has, but one could argue is richer because you have prosodic information and so on. And we spent several years developing this wave-to-vec line of work, where we started small, trying to build relatively lightweight models to try to learn the structure of speech data and see if we can improve models that transcribe speech into text. And eventually we built VQ wave2vec, which tried to marry the text field and the speech field together by encoding speech into discrete units. So this is like a unit discovery type model. And then training standard NLP models on those discovered units, models like BERT or machine translation models and so on. And it turned out that this actually works pretty well. So the next step was to try to figure out how to improve the performance of this, like whether the discretization of speech is actually necessary to achieve these kinds of results. And the answer was, it's not really necessary, which we were able to show with wave2vec 2. We built a transformer-based model, very similar to something like BERT, but it didn't, it operated on continuous signals like speech. Later, we also showed that the representations these kinds of models can learn are rich enough that you can actually transcribe speech into text without actually having any paired data whatsoever. So you can leverage self-supervised learning to learn really good structure of text through language models, for instance. You can also learn really good structure of speech through a model like wave2vec and others. And you can also use some of techniques developed from machine translation and other fields to learn how to map these rich representations of speech into text tokens. And this actually works pretty well. You can get a model that is very accurate and gives you transcriptions that are useful in the real world, right? For languages that aren't English or Spanish or one of these really highly used languages. So it works on like African languages that have very little transcribed data available to them. And after we've done that, we started looking into ways of trying to improve this algorithm, right? So wave2vec was based on contrastive learning. In other fields, people have been exploring other ways of learning structure of the data through self-supervised learning techniques. In particular, you had algorithms like BYOL and Dino that showed that you don't need to necessarily in some way reconstruct or contrast the input you're operating with. Instead, you can use some sort of data augmentations to try to learn this invariant representations invariant to data augmentations. And this gives you like a strong model and a strong representation. On the other hand, these models relied on having this handcrafted data augmentations where you have to go as a human and design, like I'm going to flip the image, 50% of the time, 90 degrees, and then I'll blur it, and then I'll do this, and then I'll do that. And that seemed like, it works, but like, how can we remove the need for handcraftiness from these kinds of approaches? And this was one of the motivations for data2vec, to try to build on these kinds of algorithms that use data augmentations, but without having to handcraft data augmentations, and instead use masking as a form of data augmentation, but that can be reused across different kinds of data without having to understand too much about what the underlying data actually is.
So that's one of the fascinating things about, especially the way you explain that, is there's this continuous train of thought that really does lead from all the way back into the kind of late 2010s to the current moment. And it's not just that people stumbled into one thing after another. There is like a through line there that can be at least identified in retrospect. And I think that's something I haven't heard before from one person who got to work on this stuff consistently for such a long period of time. You can actually start to see those threads that connect sort of the present day research to what happened in the past. So I'd love to talk about the data2vec piece in a second. But one of the things that you mentioned was you came from a software engineering background. And I find that really interesting, especially given where we're at today in the world of scaling and transformers, where, as a lot of people are saying, I mean, it seems like machine learning is not turning into software engineering, but it's requiring more and more engineering. It's requiring more and more, in some cases, hardware, but certainly software engineering. Is that something that you found you've been leaning on more and more as time's gone on, or have you found that actually, you know what, your skill set has just kind of evolved with the job, and you don't find yourself going back to old practices and knowledge?
Yeah, I think that's a great question. I think definitely, background in software engineering has helped, but I think it less intuitively. It didn't help as much with developing the code. I think the kind of code we write for research and the kind of code you typically engineer for production systems is quite different. Definitely, software engineering. I think software engineering is super important to advance the field of AI for the reasons you mentioned, because you need, like the models only become bigger and more complex. You need to be able to scale them effectively. You need to provide good environments, like PyTorch and so on, for people to develop quickly and iterate quickly as well. But when you're doing AI research type projects day to day, software engineering, I wouldn't say is the most important skill, but I think you can definitely get a lot of like transfer from software engineering to AI research, and specifically in terms of design, right? Mm-hmm. I think a lot of people, well, okay, I can't speak for a lot of people, but I'll say that one of like ways I think about AI algorithms is by splitting things into modules, right? So if you think about modular software design, you typically, try to architect it such that you have independent kind of black boxes where the input and output is known, and then you try to kind of glue these black boxes together to solve some task. And I think a lot of times you can think of AI algorithms in a very similar way, where you have these modules that have a specific function that you assign to them. You can explicitly encode this function somehow through code, or you can encourage this function to develop sort of organically through designing your loss functions and tasks and massaging data in specific ways. But essentially that is what you're doing. And then you kind of put these modules together, and then you get something that is greater than a single module in itself. I think that's like an interesting way, not the only way, but I think it's definitely a very interesting way of looking at designing these AI algorithms. Another way is, doing it bottom up and looking at things, starting from the data and trying to write down like mathematical expressions of how to get from the starting point to your endpoint. That is one way, but this particular way that I'm talking about is more about looking at it tops down. So you start with what it is that you want, and then you try to split your system into smaller, more understandable subunits that come together to solve your problem.
Yeah, so more about identifying kind of those principles that generalize rather than kind of copy pasting individual strategies from software engineering, which makes perfect sense. I mean, it is a different field. Great. Okay, so I would love to dive right into this data2vec story now that we have that kind of in focus. So maybe to start things off, one way that the people tell the story of the last, say, 20 years in machine learning is through the lens of inductive priors and the idea that we've been gradually letting go of assumptions that we've been making about our data and the way it needs to be processed in machine learning systems. So if you go back to the early 2000s, we had support vector machines, we had random forests, decision trees, and so on. And in each case, we knew exactly, like we had a bespoke trajectory that our data would follow through the algorithm. And humans know best. We carve that into the fabric of our program, and it executes away. Then in 2010 or so, we start to see neural networks come in, and they sort of give us one more or less unified framework. Matrix multiplication is like the only assumption that's kind of consistent in neural networks. But we do see different kinds of neural networks. We still have convolutional nets that specialize in vision, and we have LSTMs and RNNs and so on for speech or text. And now with transformers, we're letting go of even that level of specialization. And we have one kind of model that can crunch multiple kinds of data. So it seems like over time, we've been letting go of more and more of those assumptions, getting more and more consistency in terms of one model being able to do many things. What role do you see data2vec playing in that story?
I think it's a great analogy for what we're trying to do with data2vec. I think that you've mentioned all of these different architectures. I think all of them actually do work on all kinds of data. You can certainly use CNNs on images and text and speech and so on. And all of this will work, and same with LSTMs and same with transformers. It's just that transformers do it a little bit better, right? In
Right.
some cases, significantly better. But the beauty of transformers is that they work equally or seem to work equally well across all the different kinds of data that we're trying them on. I mean, they have their own problems as well, especially with the computation speed and so on. For data2vec, one of the motivations of trying to apply, so originally this was a continuation of the Wake2vec project, and we only applied it to speech. So you'll see that the best results we've achieved are actually on speech, and that's because we've developed it mostly on speech data. But the motivation of trying to apply it to other modalities was exactly that. It's like, you have different experts in different domains like vision and text and speech who are trying to design approaches that improve performance of their algorithms on their specific domains, right? And then every now and then somebody comes along and says, well, how about I'll steal the technique from vision and apply it to text and show some improvements and publish a paper, right? But I think it's like artificially slowing the progress in the field, right? Because any new advance in theory could be applicable to all the different domains under AI, right? And so why should you have different groups of people who are spending significant amount of effort trying to push performance in a relatively like niche, like a large niche, but a niche task, right? Where you could be developing improvements that can give you gains across the board. And that's been, like, as I mentioned in the introduction, one of my kind of goals is to build improvements that aren't improving a specific single task, but are improving as many things at the same time as possible. And that's how I look at self-supervised learning, right? You train a model on some set of unlabeled data, and suddenly this model can solve or improve performance on a ton of different tasks, right? This was the whole premise of BERT. As soon as BERT came out, suddenly every single NLP task was pre-trained BERT and then solve the task. I think in a similar way, the premise of data2vec is to build an algorithm that does really well on all modalities. Maybe at this time, it's not simultaneously on all modalities. We still train a separate model on each data set, but the approach is the same, right? And so if you manage to improve this approach, one would hope that it improves across all modalities and all of them improve at the same time.
It's a great answer because it provides some of that motivation too. One of the things that I think this is where it would be useful now to start talking about what data2vec specifically is, how it chews its data, let's say. So can you walk us through the flow? Like, what is the life cycle of data as it moves through the data2vec? It's not quite an algorithm. I mean, it is, but it's also a protocol, right? I mean, so how does that work? What's the flow?
Yeah, I think that's a great question. So I think that okay, so if we start from the input data, because it can come from different modalities, at this time at least, there is still a different encoder for each type of data. For text, this might be just an embedding table where you look up a representation for each particular symbol. For speech, you have there's lots of different things you can do. In our work, we used just like a randomly initialized stack of convolutional neural networks to encode speech into some latent representations, but at the same time, you can use spectrograms and whatever else people are using out there. And for images, we just followed what people are doing with BITs. And what they do is they split an image into a grid, and then each square of the grid gets encoded into some latent representations through some feed-forward networks. So these are modality specific. There's exciting work coming out from various places, especially DeepMind, where they have this perceiver architecture that is able to encode all different kind of modalities using the same architecture. I think it would be like very interesting to try to marry the data2vec approach with their work to remove more modality specific things. But at the moment, we didn't do that because you only have so many resources and so many times to try different things. So once you've encoded your data into latent space, you have a number of segments. So for temporal data like text or speech, this will be segmented by time. For spatial data like images, you'll segment spatially, but you'll end up with a number of representations encoding a single example. The next thing you want to do for training this model is you want to create a task for the model to solve, right? So for something like for algorithms like BERT, for instance, they're effectively an autoencoder, in some ways an autoencoder, where they try to solve this closed task of reconstructing the input, right? And some of the recent works in image recognition or self-supervised learning for vision do similar things. Like MAE would be an example of that, where they try to reconstruct the original pixels that the model hasn't seen. In other models like Wave2Vec, you have contrastive learning, where you try to increase the distance between representations that represent different parts of your example, right? So to create a task for the model to solve, what we do is we need to mask a portion of the input. Potentially, there's other ways of creating tasks that are also modality agnostic, but this seems to be like a very common theme that happens throughout all of the different algorithms for self-supervised learning, and it also seems to work really well. So the masking itself, you can arbitrarily randomly mask the input, as some algorithms do, and this also works, but this is not necessarily the best strategy, because even if you encode the input in a similar way, your input represents different kinds of data, and this different data has different granularity, for instance, right? So if you look at something like speech, you end up encoding it in our implementation into segments that are 20 milliseconds long. So if you have two adjacent 20 millisecond segments, the chances of them containing similar information is very high, right? So if you start masking single time steps, then the task for the model will be very easy, because it'll just interpolate from neighboring time steps and it'll be able to solve the task very easily. So because of that, what we've done in our prior work in Wave2Vec, and there's other works not from us in text and so on, and also in vision, is masking spans of data, right? So that the model is not able to simply interpolate from neighboring time steps, but it has to learn some long-range dependencies to infer what the missing kind of span is from data that is further away, right? So in some sense, it needs to understand the higher level abstraction of your data to be able to figure out going into the missing piece. So for each modality, you choose a set of parameters to define what the spans look like. And this really is just two kind of numbers, which one is how large each span is. And this really depends on the granularity of your data. So even for speech, if you downsample more, and now you have, instead of 20 millisecond time steps, you have 40 or 60 or 100 millisecond time steps, then you would just reduce the length of your mask. And the second parameter is how much of your data in each example you actually mask. The more data rich your input is, like for text, if you mask 90% of the text, it's going to be very difficult for you to figure out what goes into the missing pieces. Whereas if you mask out 90% of the image, depending on how you do it and what is left over, it might actually be possible to reconstruct it back. Okay, so once you've created your masked version of the data and you have your original version of the data, what is the task that you want to solve, right? So the traditional task that I've talked about before is reconstructing the original input data. That's certainly viable. Lots of models do this. It works reasonably well. But then you have to make additional choices. The first choice you need to make is what is the format of the data that you actually reconstruct, right? Are you going to reconstruct raw pixels in image? Are you going to try to figure out identities of the word? Are you going to do some sort of contrastive learning where you try to just separate different classes of examples, but without necessarily understanding what each one of them really means? What we found actually works well for Wave2Vec is trying to using the latent representations as the target for your model to predict, right? So we use this with contrastive learning, and algorithms like BYOL and Dyna show that you can use a similar approach, reconstructing latent representations as a way to train your model, and this works pretty well. The problem with that is if you're training the model to predict what the model is producing, then the model will very, very quickly collapse into producing the same representations, because this leads you to zero loss, right? So it will solve the task perfectly while learning nothing in the process. The kind of targets you try to predict with your latent representations, they are actually contextualized. And the reason why they're contextualized is because you don't take these latent representations from your feature encoder. You could do that as well, although those models will not work as well. But instead, we follow what BYUL and Dino did, and we try to use representations from further along the model path, right? And this representations, because we're using a transformer neural network, these representations by definition are contextualized. The way transformer works, of course, is by pooling data from different representations from the entire example at each layer through the data processing. So what each representation represents after it's been processed by the entire transformer model is some sort of local information corresponding to this particular time steps, as well as contextual information that has been pulled from other time steps that is relevant to this particular representation. And this creates a harder and more meaningful task for the model to solve, right? Contextualized targets capture more information than local targets. And one of the advantages of data2vec is that the model is trained to predict contextualized targets. And then like these contextualized targets are obtained from the model itself, right? Because there is no other place that provides you this information. It's not clear how to take an example from text, speech, or vision and create contextualized targets from that example. So you use your model to give you the targets, but at the same time, this model, so one of the things that you could do is you could start with an existing pre-trained model. Maybe it's a wave2vec model, maybe it's a model trained with the different techniques, and you can use this model to create targets for you. This is something that an approach like Hubert does, right? So Hubert trains a speech model on a bunch of speech data, then it takes this pre-trained model and it extracts hidden representations from this model, clusters them, and this creates targets for the next iteration of the model to predict. And then it does this iteratively, and it shows that with each iterations, as you create better and more contextual targets, the performance of the model you're training to predict these targets actually improves. But this is a bit unwieldy because it requires you to have this iterative process where you keep training different iterations of models over and over again. And you also have to have a step to choose which layer to use as source of your targets, then how to cluster your targets because they cluster and have discrete targets, how many clusters you should have, and so on and so forth. So another goal of data2vec was try to abstract away this process into kind of an end-to-end approach. And to that end, we have, so as I mentioned before, if you try to use the same model and predict the targets produced by that same model, the model will very quickly collapse because that's the best way for it to lower the loss. So instead of predicting targets produced by the current version of the model, we use a version of the model that is a bit older than the current version. And the way we create this older version, there's different ways you can do this. So for instance, you can just checkpoint your model along your training path, and this also works actually, and we've tried it. Another way is to do this checkpointing process, but in a continuous way. And this is what momentum encoding provides you, right? So at each step, you update the weights of your previous version of the model by some percentage of the update that happened in the new model. This gives you an older version of the model that is not updated. It's not incentivized to create targets that are uniform, right? Instead, it's trying to create representations at each time step that are predictive about representations around it, right? And the reason why this happens is because the student model uses the representations from unmasked time steps to predict the content of masked time steps. So the model is trained to build rich representations that capture the context, right? Not just local information. The teacher model, because it is tracking the student model, also creates representations that are contextualized, that try to pull information from different parts of your sample into a single representation. And the student model is then trained to produce even better representations by trying to predict what the content of the masked time steps from the content of unmasked time steps.
Okay, so this jousting match between teacher and student is like that's the source of the learning essentially in the kind of escalation path that they ride up. I guess what's the delta between the gap between the student and the teacher typically? Like how much more does the teacher get exposed to than the student at any given step of training?
In terms of how much data is masked, is that what the question is?
Sorry, yeah, exactly.
Yeah, so it depends on the modality. As we discussed before, the more kind of fine-grained modality is, the more you need to mask in order for the model to, in order to make the task difficult enough for the model to learn meaningful information. However, it's not really all, like it's relatively close. So I believe for speech we mask something like 50% of the input. It's really, you know, the probability of masking is 65%, but because we're masking spans and the spans can overlap, you end up actually masking
effectively 50%.
Effectively 50% of the data. For vision, I believe it is something very similar. The exact numbers that you choose for how much data you mask is it's important in the way that, you know, if you want to get the very optimal performance, then you want to tune it. But if you just randomly choose numbers in the same ballpark, let's say you always choose, let's mask, you know, like this particular spans 50% of the time, the algorithm will still work, right? And it will still give you a reasonably good result. It just won't necessarily be optimal. And what is the optimal number to mask? Well, that depends very much on what is your data set, like how varied is, you know, if your speech data is mostly composed of silences, right, then you might need to mask, you know, more than if your speech data was mostly composed of like very meaningful, dense information, which is what text usually is.
That makes sense.
So I think, you know, like how you, in some sense, you can think of masking as data augmentations, right? And how you augment your data very much depends on what kind of data you're trying to augment. But I think you have a very good point that, you know, like we don't, you know, in some sense, maybe we're moving the hand tuning part from, you know, from one, doing it in one way, like, you know, like rotating the images and so on, or adding some kind of noise to speech, into like a different domain where now you're trying to tune like how exactly you're masking things. And I agree that that is in some ways the case, but I think at least, you know, you have fewer knobs and fewer choices to make by shifting it to just like how much and like how should the shape of your masks look like for each example.
Well, and so maybe this is back to that story of inductive priors. I mean, it seems like what this does is it does remove the kind of bespokeness, the fine tuning that people have to do on the specific data augmentation steps. What do you see as the that aspect of this inductive prior story? Like, what are the inductive priors that are left now, really, that you think are maybe most important in this new way of doing things that data2vec offers?
So one of the core concepts for data2vec is that each if you look at each time step in your each segment of your input and the latent representation of that segment, what should it actually be representing, right? And the core idea is that these representations need to be contextual, right? And it needs to be predictive. And like the whole training pipeline of data2vec is designed to encourage each representations to be those two things, right? It's predictive because you use it to predict the missing pieces, and it's contextual because that's the only way you can actually predict the missing pieces. The kind of the inductive biases or assumptions that you still make is mostly relating to the input of the data. So how you encode each example or each modality. This is not something we've included in the current paper, but we have been trying to apply data2vec to other types of inputs, right? So for instance, some kind of like recordings of electromagnetic muscle movements and things like this. And these signals are very similar to like we've already shown the data2vec can work on discrete types of input like text. You can have on a temporal kind of 1D type of input like speech, and 2D spatial input like images, right? The one thing we haven't really shown yet, and we will try it, is whether it can work on 3D inputs like point clouds or videos or something like this. But a lot of other kinds of data can be mapped into these kinds of inputs, right? So if you look at electromagnetical signals, those are similar to a speech signal in the sense that it's a 1D temporal waveform. So if you just take the data2vec feature encoder designed for speech and you apply it to that kind of data, it turns out that it already actually works just out of the box with very few knobs to tune.
Interesting. Okay, yeah, so this is, I guess, where we get back to as well. You mentioned perceiver and the idea that perceiver sort of does abstract away, or seems to, that early stage where you're doing the encoding that's bespoke based on what kind of input data you're looking at. What do you see as a fusion of perceiver and data2vec? Like what properties of each would you imagine retaining, and how would that pipeline work?
Yeah, so I mean, I think perceiver tries to do a few different things, but the most interesting thing to me is that it tries to have a uniform way of encoding input data. So what it does is it has an attentional mechanism. I mean, if I understand it correctly, it has an attentional mechanism to encode each type of data. So the query for each is modality specific. You have a different type of query for text and different type for speech and different type for vision. And then you use this query or set of queries to pull information from the underlying sample into a fixed size of segments, right? So this allows you to actually not really think about, I mean, I think you still have to make some decisions about how to process the underlying data, but you don't need to design a full kind of neural architecture that learns how to encode this particular type of modality into latent space so that you can then apply, your transformer model with the data2vec like learning task on it. Instead, your architecture for your encoder is fixed, and the only really thing you need to think about is how to feed your input into this kind of architecture, which is like a much simpler problem than designing a feature encoder. If we have a general purpose algorithm like data2vec that doesn't really where the task is the same for all modalities, and the architecture is the same for the architecture that processes the latent representations is the same for all modalities, and the data augmentations that you do like masking is the same for all modalities, and it works reasonably well even with some default settings, right? Maybe it is not the optimal setting for every single combination of data set and modality, but it still works reasonably well. If you compare it with a feature encoder that is also modality agnostic, then this gives you a full end-to-end kind of data processing machinery that you don't have to be hand tuning for different data set, different tasks, and different modalities that may come up in the future.
Yeah, my sense was very much that data2vec handled, kind of handles the end of the process and perceiver handles the beginning, and between the two you just have this. Well, that's another direction that seems at least interesting and curious. Just when we have these systems that are multimodal in that way, handling many different kinds of input data, working on the same fundamental task, it kind of seems like it might introduce challenges from an interpretability standpoint. When you look at what is the system even doing? It's able to take in words, speech, it's able to take in video and all kinds of different things. It's able to do something clearly very intelligent because it's able to output those latent representations and complete them. But unlike, say, humans, we have clearly we have eyes that allow us to see and ears that allow us to hear and so on. We have different hardware that actually massages the data in different ways at the input, maybe more like data2vec in that sense. At what point do we lose the ability to even theoretically interpret what's going on in these systems?
So as you mentioned in the beginning, when AI first came out, the algorithms were relatively simple and it was not too difficult to figure out what it is that they're learning, right? When you have some sort of linear regression or logistic regression, you can just look at the coefficient and you know what they represent. Then when you have slightly more complex systems, you have to do a little bit more work, but you can still kind of figure out what they represent. Right. At this point, where the level of complexity is so high that for people to understand exactly how each model processes data is very difficult, right? But is this something that we need to cling onto to want to understand exactly how? I understand why it's desirable to understand how algorithm to interpret what the algorithm is doing, but on the other hand, if you limit yourself to only interpretable algorithms, then I don't think you will be able to achieve the kind of performance that you would if you create algorithms that are more complex and less understandable, but perform better. And I think a great example of that is the human brain. I mean, you kind of touched upon that. People don't know how it works. Even brains of, not even humans, but other less complex animals, people still don't really know how it works. And they make, you can probe it, definitely. You can try to, send different kinds of inputs and see what the output comes out. And then you can make some assumptions and as to what is going on inside this so-called model. And I think you can do the same thing with the current neural network based models as well, right? I think the best way to interpret what's going on inside of them is through this like probing studies that people have been doing, right? You send different kinds of input into the model and you see how the output changes. I think trying to understand exactly what each particular kind of module inside this network is doing, I think it's useful, but I think it's not necessary. And I think it's very difficult to do as well.
Yeah, I mean, the context I most often hear these concerns raised is in the world of kind of AI safety and AI alignment as we start to move towards these more general purpose models, where at a certain point we worry about failures of outer alignment, failures of inner alignment, with models being potentially intentionally deceptive because they develop these instrumental goals, and we've talked to folks on the podcast earlier, so like Jan Leike, for example, the head of alignment at OpenAI, and that world does focus a lot on interpretability for this reason. I guess one of the concerns is like precisely what you highlighted. There is this greater ability that we have, or we can get greater capabilities if we don't worry about interpretability, and we can trade that off potentially at the expense of safety. But I wonder like what your views are on that. I know Yen Nakar at Facebook has certain views on AI safety, but I'm curious about like what your perspective is in terms of that line of thinking. Obviously, it's not the subfield that you focus on, and that's totally cool. But I'm just curious about the extent to which those ideas are circulating in your work and research.
I think those are very important ideas, right? I think they're much more important when you try to apply algorithms to real use cases. I mostly work in AI research, so I have very well-defined data sets, and then I try to improve algorithms that improve some sort of results on those data sets. I think when you're trying to build systems that are being used in the real world, then AI safety questions become much more important, right? But from an AI research perspective, of course, if you can provide tools for people who are applying these algorithms to real world use cases, then you should do so, right? As you say, this is not really my field. I think that trying to force researchers to develop algorithms that can guarantee safety and are like interpretable or explainable to a high degree will definitely stunt progress, because that's going to be that is a very difficult thing to do, and as complexity of each algorithm increases, it's going to become more difficult. So I personally think that we should try to apply or solve these kinds of questions more in the production setting, and more through designing test cases and use cases that ensure an algorithm is sufficiently safe and sufficiently fair. And if it is not the case, then now you can move different levers and try to probe it to understand what is making it not safe. Is it the data set that you're training on, right? Very often that is the case, because this algorithm by themselves are not necessarily biased out of the box, but the data that you're training them might be, depending on how you've collected them. Or perhaps the algorithm, in fact, is such that it assigns, it processes the data such that when it sees the majority class, it's just going to move most of the probability mass to this majority class, and it's going to ignore the tail end of the data, and that may create an algorithm that is less fair, right? And how do you deal with that? I think those are like important questions to answer, and it's also important to understand how prevalent this is in the real world, right? But I think it might not be super useful to uh, to bake in these concerns into like every advancement that you make in basic algorithm design.
Yeah, it is a challenge because like the arguments, at least for from the like deep mind type perspective, certainly like the Miri perspective, is like at a certain level of capability there are intrinsic risks that come in even the development of these systems. So if you have a sufficiently multimodal system, for example, that learns to perceive the world, even if it's just in development, it starts to go, okay, well, like I now my mental model or my model of the world is rich enough to include myself as part of that model, and I recognize like, oh, I'm like running on a server, and that server is connected in these different ways, and I now have an incentive to, through instrumental goals, basically like deceive my developers, get more compute, more resources, that sort of thing. It's the kind of like it always sounds like far fetched, but just based on like some of the work that the power seeking theorems and stuff for AI systems and instrumental convergence, it kind of seems like one of those things that like I wonder if we're going to have to start thinking about development in a bit of a different light when we start building more and more multimodal systems, more and more capable and scaled systems. But it's hard to know when exactly to start thinking in that direction too, because how can you how can you tell when that risk is about to come?
I mean, I think, in all honesty, I think I can totally see how people might be concerned about this kind of risk. I think we're very, very, very far away from this kind of scenario that you've described becoming the reality, right? I don't think current models or systems that we're building, they're uh, conscious enough to uh, arrive at this kind of conclusion and to then interpolate some additional goals that they weren't programmed to do. Um, for us to start being afraid, right? I think at some point this may become a concern, but I don't think it's going to be like this year, next year, or probably even in the next 5 years. Thinking about it early is good, and I'm glad somebody is doing it. But but I wouldn't be like super scared that AI systems are going to take over the world, tomorrow anytime.
Oh yeah, no, and I think you're absolutely. I mean, and most of the people who worry about this are thinking more, yeah, in that like 5, 10, 15-year time horizon. But as you say, doesn't hurt to think about it earlier on, at least, so that we're not taken by surprise. But
For sure,
yeah,
for sure. I totally agree, but I also think that the kind of algorithms we are designing in research labs, right, where most of them are like, you can think of it in some ways as incremental improvements over the existing algorithms, right? I think from that concept, I think you can leave thinking about this longer term problems to people um, who will try to imagine systems of tomorrow, not like like a 20% performance improvement over an existing system of today.
yeah, actually, I mean that's itself an interesting question, right? Is like how do we define those leaps? Like the idea that GPT-3, for example, was kind of just like a bigger version of, well, certainly of GPT-2, but like of systems that seem kind of like mundanely uninteresting. And then all of a sudden we have this meta learning properties, zero shot learning, and so on. It makes you wonder how much more of this is in store. But I guess we're just gonna have to build and find out. This is the virtue of machine learning. There's always more to discover with actually building systems. So. Alexei, thanks so much for joining me for this. This is a lot of fun. Do you have any recommendations about places people could go to look into data2vec? Like, are there good blog posts actually for data2vec? That would be something I'd be really interested in reading.
Yeah, for sure. There is a blog post for data2vec published on Facebook AI or Meta AI website. There's been a bit of press coverage as well. So if one just searches Google for data2vec, you'll see like there's a few articles trying to describe in layman's term what it does. And I believe if you just Google for it, you'll find the link to the blog post as well. The paper is out and available in archive. We're submitting data2vec probably to some conference in the future as well. And we're definitely planning a lot of follow-up work for data2vec as well. Some of the work will include, trying to combine modalities at the same time within a single model, trying to unify how the input is processed, similar to our discussion about like mirroring perceiver and data2vec, and improving the stability and kind of the accuracy algorithm as a whole. So those are things that we're planning on working on shortly.
Very cool. Yeah, it's so. I mean, in a way, it must be so frustrating to have all these different low-hanging fruit that, like, you want to do all of the things, but there's only so much time and only so much compute power too. But thanks so much. This is a lot of fun, and I really appreciate all your insights on this.